Okay, this is our momentum review. So we're going to go over each of these questions now. They're in a weird order because I clipped these questions from released AP tests. So your test that you take will have these, not these questions, but we'll have questions from AP tests on it as well. So I wanted to give you as many of those as I could, I guess, so that you would be ready for that level of question. So we'll go through each of these. What I'd like you to do on the review, again, like usual, is to work out the question first, or at least attempt to work out the question, then check the answer, maybe work it out again, then watch the solution. I think by just watching the solutions, you're not going to do yourself any favors. You're just going to watch me solve problems, but I can't do that for you on the test, so you may be in a bit of a tight spot. So keep that in mind. So with this question, we've got a student standing at one end of a raft floating in a pool with equally spaced marks along the bottom as shown. So the student and the raft have the same mass. The student walks to the opposite end of the raft. Which of the following best shows the final locations, assuming there's no drag force between the raft and the water? So this may not have much to do on its surface with what we've done with momentum so far, but this is a momentum question. So looking at the student on the boat, because there's no friction with the water, there are no external forces acting on this system. And one of our big ideas, one that you need to pick up on a lot going through this, is that if there's no net force on the system, then the velocity of the center of mass of the system remains the same. So there are no net forces here, which means the velocity of the center of mass of the system is going to stay at zero. They're at rest to begin with, so the velocity of the center of mass is zero. So right now, with the velocity of center of mass being zero, and it's staying that way, that means the center of mass is going to stay in the same location the entire time. So the boy's center of mass is wherever the student is, and the boat's center of mass is in the middle of the boat. The center of mass of the system is in between the two of them. So I'm going to draw a long line down through all of the answer choices where the center of mass of the system is. So there's my long line. Now, if the center of mass of the system doesn't move, then it's always going to be there. The boy is going to walk to the other end of the boat, and the center of mass of the system is going to stay on that red line. Now, no matter where the boy is, the center of mass is going to be in between the boy and the center of the boat. The only place we see that happening is choice C. So if we want to write down our explanation for the answer to kind of summarize all the things that we've just said, what we're going to say is the net force on the system is zero. The net external force is zero. And so the velocity of the center of mass is initially zero, and it will not change because the net force on the system is zero. No net force, no change in velocity. That means the location of the center of mass is going to be the same. It also will not change. It's going to be in the same spot. That's why we drew that line all the way down the middle. And I know that the center of mass has to stay in between the boy and the middle of the boat. So the only time that position in between the boy and the middle of the boat is on my red line is for part C. All right, the next one, we have this graph of force versus time for a spacecraft. Now, looking at a graph of force versus time, we know that the area is going to be the change in momentum. And if I want to know the change in speed, knowing the change in momentum is going to be a super helpful thing for that. So it's kind of a rough graph. We're going to have to make some estimates because we're estimating what's going on. So we're not going to get perfect numbers, but we can get real close. So if we look at this graph, what we want to do is draw a line that kind of represents what the force is doing the whole time. This is a pretty good representation of that. I got a little triangle from 1,000 newtons to 2 seconds, and then a little square down there from 3 to 4 seconds at 500 newtons. So the thing that we know is that the area is equal to the change in momentum. So for this first one, there's a triangle, so I got 1/2 the height, 1,000, times the base of 2. That makes that area 1,000 kilogram meters per second, because it's the change in momentum. Down there, the area is just negative 500 times 1, so that area is negative 500 kilogram meters per second. Those are my two changes in momentum that I get from those different parts. So the total change in momentum for this system will be 1,000 minus 500. So the change in momentum is 500 kilogram meters per second. So mass times change in velocity is 500. So that change in velocity is 500 over 4,000, which is roughly 0.125. So if we want to walk through the answer, just to summarize, the area of that force versus time graph is the change in momentum. The area total was very close to 500 kilogram meters per second. So change in momentum is mass times change in velocity. The change in velocity is the change in momentum over the mass, or about 0.125, which is really close to 0.1. That's why we chose 0.1 for our answer. All right, for our next question, we have this train that is traveling with a constant speed of velocity of the train. We got two spheres in the train. They got the same mass. They're identical. And they're moving towards each other with the same speed, Vp. Sphere, I guess, because there's a P in there. So, and they're moving like they're shown. What's the velocity of the center mass of the spheres in the frame of reference of the train and in the frame of reference of a person standing outside of the train? So if I'm in the train and I'm looking at that, the velocity of the center of mass is going to be 0. They cancel each other out, which means they're moving with the train. And then outside of the train, it looks like the center of mass is at rest with respect to the train, so it's moving with respect to the train. The answer is not A. Sorry about that. The answer is B. I can fix that. So, all right, to an observer in the train, each mass, each object has equal speed in the opposite direction. What that does is gives me a velocity center of mass equal to 0. So I got mv minus m times negative v over the sum of the masses. It's 0. So with respect to a person in the train, the velocity of center of mass is stationary. It's moving with them, with the train. To an outside observer, all stationary objects inside the train are moving with the speed of the train. They have the train's speed. That's why that's going to be Vt. So the answer is B there. Sorry for the confusion earlier. All right, so for this next one, in a one-dimensional, perfectly elastic collision, an object of mass m, driving speed v0, hits an object of 3m that's at rest. So, one thing I want you to think back to is the collisions that we did in the lab where we ran the objects into each other. If it's elastic, that's the same thing as magnets facing magnets. And what we noticed with that is when a light object hit a heavy object, the light object bounced backwards. The only one that's going to show that, with that object of mass m moving backwards, is part D. So that's the answer. Now, so we're going to write that kind of line of logic down first. In an elastic collision, a moving lighter object will bounce back when it hits an object with more mass, when that mass is stationary. That's something that we saw with the magnet versus magnet collision. Another way of looking at this problem is that we know momentum has to be conserved. No matter what kind of collision it is, momentum has to be conserved. So initially, the momentum of the system is mv. So at the end, the momentum has to be mv. So if we look at A, the only thing moving afterwards in that one is 3m, traveling at v0 over 3. So that makes the final momentum mv. For B, if we do the same thing, we've got mv0 over 4 plus 3mv0 over 2. That momentum is 7mv0 over 4. So momentum is not conserved in B. That's not even a possibility. For C, if we do the same thing, we've got mv0 over 2 plus 3mv0 over 2. That makes my final momentum 2mv0. That's too big. I can't gain momentum in a collision, so that's out. If we look at the last one, we have negative mv0 over 2 plus 3mv0 over 2. The final momentum is mv0. That gives me an actual collision. So the choice is between A and D because B and C don't show conservation of momentum. So the only choices we have are A and D. And if we remember back to those objects colliding, the only way for the first object to stop with the elastic collision is if it hits something with the same mass. All right, so A and D are the only ones that show conservation of momentum. And choice A shows that initial mass stopping, and that only happens when they runs into an object with the same mass in an elastic collision. Let me get that all written down. Sorry about that. Now, let's move on to this ice skater moving at a constant velocity. Sorry, I got to catch up. All right, so an ice skater moves constant velocity across a pond. Skater throws a snowball directly ahead. Which of the following describes the velocity of the center of mass? Well, if we're on that pond, and the net force on this ice skater is 0, friction and air resistance are negligible, so there's no outside forces, then the velocity of the center of mass of the system has to be the same before and after something happens. So the velocity of the center of mass of the system is the velocity of the skater before something happens. So the velocity of the center of mass after she throws the ball is going to be the same as the original velocity of the skater. I'm just going to kind of summarize that right there. The net outside force on the skater snowball system is 0. Which means the velocity center of mass will remain constant. It has to be the same as the velocity of the skater to begin with. Now, for this next one, the data in the table were recorded during an experiment where two carts ran into each other. We got change in momentum, acceleration, mass, and force. So for cart 2, we want to know the change in momentum. Well, when things collide on a frictionless track, and there are no outside forces, then the change in momentum of object 1 is the same as the change in momentum of object 2. So since they have the same changes in momentum, my answer choices are going to be A and B. Now, between those two, we've got conservation of momentum. For the last part, if I want the acceleration, well, I know that acceleration is equal to force over mass. And so for cart 2, the force is 15 newtons, the mass is 1 kilogram. And so the acceleration is 15 meters per second squared. That's choice B. For these next questions, we've got this graph of velocity versus time. It's for the next 2 questions. We're going to explain the answer to both of them. So what this shows, what the graph shows, is that initially the velocity of the center of mass of the system is 8,000 meters per second. And after they pull each other together, it shows the velocity of the center of mass of the system to be 8,005 meters per second. Because they're moving together at the end. Both ships have the same speed. So after this collision, with the final velocity of center of mass not being the same as the initial velocity of center of mass, if the velocity of center of mass changes, there must be an outside force acting on this system. There must be a rocket firing with just one of these. That's my idea. The velocity of center of mass didn't stay the same, so there must be a force acting on it. So the answer to question 35 is yes, one of the ships has their engine on because the momentum of the system increases. Now, if we go on to the next one, to 36, I want to know what's going on with the force. Well, if I look at the velocity of center of mass for each little data point, what I see is a line that shows a constant increase in the velocity of center of mass. So the velocity of center of mass increases at a constant rate. What that means is I have a constant slope for velocity of center of mass versus time. Constant slope means I have a constant acceleration. Constant acceleration means I have a constant force. So if I have a constant force that's speeding me up, the only graph in 36 that shows that is C. And so the answer choice there is going to be C. Right, for 13, I've got two blocks moving towards each other. They're going to hit. And I want to know the magnitude of the force exerted on block B when I know that the magnitude of the force exerted on block A is F. These are two objects interacting. It sounds like a Newton's third law question, and it is. Block A experiences a force F because of block B. So block B experiences a force F from block A. Third law question. When two objects interact, the force on one object because of the other object, the force on A because of B, is going to be the same as the force on B because of A. So that net force has to be equal. We can't lose sight of that Newton's third law thing. Next one. A lump of clay is sliding to the right on a frictionless surface. Oh, actually, I'm going to do the next one. All right, so if we look at this graph of force versus time for tennis ball, what we know for a force versus time graph is that the area is the change in momentum. So 1 millisecond is 1 to the negative 3 seconds. So that area is 5 Newton seconds. That makes the time. So we take 8 milliseconds times 500 newtons. That gives me a change in momentum of 5 Newton seconds because the area is 5 Newton seconds. And what we see here is that that force is positive. It shows me an increase in momentum. So looking at the tennis ball, it's moving to the left to begin with. That means the initial velocity of the tennis ball is negative 10 meters per second. The racket pushes forward with that positive force, giving me a positive change in momentum. So mass times change in velocity is change in momentum. Mass times V final minus V initial is change in momentum. So V final minus negative 10 is equal to positive 5 over 0.05. So we kind of divide 5 by 0.05, get 100. We apply those negative signs. So V final plus 10 is equal to 100. That makes V final 90 meters per second. Then if we come up here for our lump of clay, it's sliding to the right on a frictionless surface, speed 2 meters per second. It hits and sticks to a metal sphere. We're going to ignore this because it's asking about kinetic energy. So we're going to ignore number 15 altogether. Sorry about putting that on there. All right, so for this question, we have a jagged graph of force versus time. What I want to do is clean that up a little bit so that we can do some estimating to really see what's going on. So that's what we got. Now, I know that the area of a force versus time graph is momentum, is the change in momentum. So what this graph shows is that for every time interval, my momentum is increasing. There's never a time when the momentum stays constant because I'm always getting more area with this graph. So that means answer choice A and B are out completely because A shows constant momentum for 2. That doesn't happen. And B shows 0 change in momentum for that second area. So that leaves me with C and D. So what we have to look at here is sort of the rates of increase. So if we look at 1, the rate of momentum change, or the rate of momentum increase is only constant for 2. And so if you look at C and D, it's only constant for interval 2. So that's the only one that should be a straight line. So D shows sort of a curve and then a straight line with positive slope and then another curve. That's what our force graph shows. So our answer is D. So these other questions are not from an AP test, but they're good things that I want you to know. So for an inelastic collision, we're going to look at these things. That's false, right? We can't change our total mass, so that's not true. Total energy is not conserved. That's also false. We haven't talked a lot about energy yet, but I'm demonstrating a point. Our rule for energy is that it's always conserved. Always conserved. We can't gain or lose. We can't change the total energy, so that's out. Same with linear momentum. We know in this collision, momentum has to be conserved, even though these objects hit and stick together. For all collisions, momentum is conserved. And then the change in momentum is less than the total impulse. Well, but by definition, the change in momentum and the impulse have to be the same. That's what they are. And so the only choice that we have is that kinetic energy is not conserved. And that's what happens. We haven't talked about those yet, but I really wanted to go through the what's not true choices. Complete the following statement. Momentum will be conserved in a two-body collision only if the net external force acting on that system is 0. That is the only condition that we have. If the net force on the system is 0, the velocity of center of mass is constant, and momentum is conserved. That's our rule. That's a big thing that you need to hold on to. Number 15, looking at this, we have a ball coming in at 20 meters per second. It gets hit by a bat and leaves at 29 meters per second. That means the change in velocity is 49 meters per second. Because it's final, 29, minus initial 20, but one of those is in the opposite direction, so we have to throw in a negative sign. So negative 29 minus 20 is 49 meters per second. So once we have that, I know that impulse is mass times change in velocity, so 0.11 kilograms times 49 meters per second gives me 5.4 kilogram meters per second. With number 6, I have 2 balls that are thrown up against a wall. With equal velocities. The first one rebounds with a speed equal to its striking speed, and the second one sticks to the wall. And I want to know the impulse that the first one transmits to the wall. So impulse is change in momentum. Change in momentum is mass times change in velocity. The first ball has a greater change in velocity. So for the first ball, the change in velocity is its rebound velocity, negative v, minus the initial velocity, v. Just like we did before, because they're moving in opposite directions, I have to throw a negative sign in there. So that makes its change in velocity negative 2v. So its change in momentum is going to be 2mv. For ball 2, the change in velocity is 0 because it hits and sticks to the wall, minus its initial velocity v. So its change in velocity is v. And so the change in momentum is mv. All right, and then for this last one, we have a boy running onto a cart as shown. It's initially at rest. This is a basic conservation of momentum thing where we're going to find an unknown. All Our unknown in this case is going to be the mass of the cart. So, doing our conservation of momentum, beforehand I have the mass of the boy times his velocity plus the mass of the cart times 0 is equal to, since they stick together, the mass of the boy plus the mass of the cart times the final velocity. So we're going to plug in numbers. 50 times 10, that's the boy, plus 0 is equal to their combined mass, 50 plus m, times v final, which is 2.5. So we got 500 equals 50 times 2.5 is 125 plus 2.5 m. Subtract 125 from both sides, so 375 is equal to 2.5 m. That makes the mass equal to 150. So, the big idea here is using conservation of momentum to figure out what's going on. Then it's a matter of solving for our unknown. But that's the basic way that you're going to figure out what's happening in a collision. Look at the momentum before, set it equal to the momentum after.